Hey guys, make sure you find the worksheet that says similar polygons on the top. We're going to talk about what makes polygons similar. Similar means that they are the same shape, but they have different sizes. So they may not necessarily have the same side lengths. And we're going to talk a little bit about how their side lengths are proportional in just a second. So we definitely have the same shape. So a square and a square, or a triangle and a triangle. And we're going to really focus on some triangles in this unit. But at first we're going to talk about just any kind of shapes. So they have the same shape, but their sizes are different. Polygons are similar if two things have to happen. Their corresponding angles have to be congruent. Remember, corresponding just means if I were to cut the shapes out and stick one on top of the other, the angles that land on top of each other are called corresponding. So corresponding angles are congruent. And corresponding side lengths are proportional. Corresponding side lengths are proportional. And of course, we already talked about a congruent statement. That would be like triangle ABC is congruent to triangle DEF. That's a congruent statement. Well, we're not talking about congruent triangles this time. We're talking about similar. So we need to talk about what a similarity statement is. A similarity statement would be triangle ABC is similar to triangle DEF. That is a similarity statement. So one means congruent, the other means to be similar. So just make sure that you are using the correct symbol when you're talking about congruent or similar. All right, so here's an example. We've got NPQR is similar to UVST, and this is just a quadrilateral because it's got 4 vertices, it's got 4 sides. And they want us to list all the pairs of congruent angles and write a proportion that relates the corresponding sides. So I really like to focus in on the similarity statement because that helps me organize my angles, especially when these things are not the same size and things have been flipped and turned or rotated. So if I look at my similarity statement, I can see N and U are in the same place. So that tells me that angle N is congruent to angle U. And remember, angles are congruent. And then P lines up with V, so angle P is congruent to angle V. And we did this with congruent triangles. Q lines up in the same place as S. And last we have R is congruent to angle T. So those are my congruent angles. The next thing we need to write is a proportion that relates the corresponding sides. Again, I like to look at my similarity statement. It helps organize which sides are corresponding. So if I take a look, NP are the first 2 letters of the first figure, and they line up with UV. So side NP and UV are corresponding, so we set up a ratio. And of course, if we say ratio equals another ratio, that becomes a proportion. My next side I can talk about is PQ. So if I look in my letters at PQ, and that lines up with VS. So I'm just using that similarity statement. I never even look at my pictures of the figures because I think that can be very confusing. So I look at my similarity statement. All right, so the next side I can use is QR. QR corresponds to ST. And then last but not least, you have the first letter and the last letter, and R corresponds with the first letter and the last letter of the other polygon. So that's what it would look like if they ever asked you to list the congruent angles and to write a proportion that relates the corresponding sides. And then from there, we can use this to solve problems, which we will. Scale factor, we've talked about that before when we worked with dilations, because really dilations is making something bigger or smaller, so then therefore we have similar figures. All right, so this is a ratio of the lengths of the corresponding sides of two similar polygons. So basically, after you've set up your proportion of your corresponding sides, any one of those ratios, you can reduce it and it would give you the scale factor. How did your figure get bigger or smaller? So let's take a look at an example. I've got two triangles here. Clearly one's bigger than the other one. So we want to determine whether the triangles are similar. And then we're going to write a similarity statement. Actually, this one we can't determine because I don't have any angles marked. We just want to write a similarity statement, and then we need to find the scale factor. So this one wants us to find the scale factor. I was looking at the wrong problem. All right, so to find the scale factor, you would obviously see that AB and XY are the only sides that they have provided. So I would set up a ratio. I could say 6:3, and that gives me 2, which is my scale factor. Students say, well, what happens if I decided to say 3:6 and get 1/2? That would still be considered the scale factor because they did not tell me to compare which figure to which, so big to small or small to big. So 2 or 1/2 would actually work in this case. All right, the second example says determine whether the triangles are similar. If so, write the similarity statement and the scale factor. So here I have to check all my angles to make sure they're all congruent. So N is congruent to R because they have the same tick marks. Q is congruent to S because they have the same tick marks. And we talked about, we hit it really quick with that review packet for the last section, that if you have two angles in a triangle congruent to two angles of another triangle, then it's understood that the third angle is congruent, and that is the third angle theorem. So all angles are congruent. So I'll make a little note down here. Angle P is congruent to angle T because of the third angle theorem. THM is an abbreviation for theorem. All right, so I got all three angles congruent. Now I just have to make sure my sides are proportional. So what we're going to do is we're going to set up a extended ratio and to make sure that they're all equal. So I would say that you have to be careful here because you have to find your corresponding sides. There's a trick to it. You take your shortest side, put it over the other triangle's shortest side. So if I take a look at my big triangle, my smallest side is 11.5. This is my smallest side. So my second triangle, the smallest side is 9.2. So they are corresponding because they're both the shortest sides. Then the middle length would be 12.5 and corresponds to the 10. So 12.5 is the next biggest and 10 is the next biggest. So I just set up another ratio. Then last but not least, 15 is my longest side over 12 of the other triangle's longest side. So now I have to determine, is this ratio true? The easiest way to do that is to put this in the calculator and convert it to a decimal. So 11.5 divided by 9.2 gives me 1.25. Do the same thing for each of these. That's also 1.25. And this one is also 1.25. As long as they're all the same, then they are proportional. And that is my scale factor as well. So yes, the triangles are similar. And the scale factor equals 1.25. And then it tells me, if so, write a similarity statement. So I still need to put my similarity statement in here, which I'm running out of room. I'll just put it up on top. So I can say triangle NQP is similar to triangle, and you have to line up your letters. So N corresponds to R, Q corresponds to S, and P corresponds to T. So that is my similarity statement for that example there. All right, so to determine if figures are similar, angles must all be congruent and the side lengths must be proportional. Easy way to do that, set up your ratio, reduce those ratios, or write them as decimals and see if they match. If they match, then they are proportional. Okay, let's flip this paper over and see how we can use scale factors and proportions to solve problems involving similar figures.